Okay, in question 2. So now we look at this Q to A. Okay, so they give you the complete triple integral. So you can have the information about the solid and the region from the given limit. Okay, so as we know that here you have the xy solid. So you have the xy solid, right? And then from the x and y limit, you can determine the region. So x is constant, where given by -2 and 2, and y is function negative square root of 4 minus x squared to positive square root of 4 minus x squared. Okay, so now we want to determine the region. So from these two equations, you can see that they can be written to be plus minus square root of 4 minus x squared, where y can be positive and negative. And when you rearrange, so you will get y squared plus x squared equal to 4. Okay, so you have a circle with radius 2. So when we sketch the region on the y-axis plane, and basically it is part of the circle centered at the origin, radius 2. So now we want to shade the area, so then from there we can determine the theta. Remember, we have to solve in spherical, we only interested on finding the theta. Okay, so to get the theta, then we have to look at a limit here. So we need to find the region that need to be shaded. So we can see that x constant, so we have the vertical line. So the line is lying between -2 to x, -2 to x equal to 2. So x can be negative, x can be positive. And y here can be negative and y positive. And all of them are part of the circle. So which means that your lower bound and your upper bound of y are at the order quadrant. So we can say that the shaded area is all over the circle with radius 2. So from here we can determine the limit of theta from 0 to 2 pi. Okay, so now we want to get the solid. So the solid give you the limit of z. So z is lower bound is square root of x squared plus y squared, and this one is a cone. Okay, so that's what I told you before. You have to profess, okay, you have to familiar with the surface that you have learned in chapter 1, so that you can imagine the surfaces that lying in the triple integral limit. Yeah, I mean that you can determine straightforward. You can just find out the surface, or you can just determine the surface directly, okay, without thinking so much, and it takes so much time to solve. Okay, so we know this one should be a cone, a standard cone, which means that your phi, as I already show you, what is the phi for this? So this phi, this particular equation of the cone will give you phi equal to, or some people say phi, okay, whatever phi or phi, doesn't matter. So the phi is equal to 45 degree or pi over 4. And this one, what is this? So just take a look. So z is equal to square root of 8 minus y squared minus x squared minus y squared. So this one, if you don't, you're not sure, then you have to rearrange, but you have to bear in mind that it's always positive. So z squared plus x squared plus y squared equal to 8. So you have a sphere with radius square root 8. Okay, this one is a sphere and this one is a cone. So your solid, if you sketch, so your solid, your lower bound is okay, firstly I will draw the sphere first with radius square root 8. So I have a sphere, but having sphere, because z is always positive, so hemisphere, where the radius is square root 8. This one is supposed to be square root 8. This one is supposed to be square root 8. So this one z, this one x, this one y. And where is your cone? So your cone, you have a standard cone, so this is your cone. Okay, and as we know that the phi is equal to pi over 4. So meaning that your solid is ice cream cone-like surface. What I mean by ice cream cone, so we can just erase this first. Okay, so where is your ice cream? So the top here, part of the sphere will give you an ice cream, and the cone here, part of the cone, the ice cream cone is part of the cone. So the combination of the cone and the ice cream, we call this as ice cream cone-like surface. Okay, so in spherical, if your solid is ice cream cone-like surface, or hemisphere, or sphere, or part of sphere, or you have a larger cone, larger ice cream cone surface, so all the limits should be constant. Okay, so now back to the question here. So we have got the region, and at the same time we can determine the limit of theta. So now from the solid, where the limit given here, so we know that we have a ice cream cone-like surface. So from there you can determine the limit of rho. So 0 to square root 8. How can we know that? So just like R, you have to sketch the straight line starting at the origin and passing through the solid. So the smallest row is 0 and the highest row is square root 8. So your row is 0 to square root 8. Okay, and then what is the limit of phi? So the limit of phi, again, look at your cone. So phi is always tell you the cone shape. So the cone is given by this equation, where this equation always equal to phi equal to pi over 4. So since your cone is exactly passing through or lying along the z-axis positive, so your smallest phi should be 0 and the highest phi is pi over 4. So then we plug in to the integration. So now our integration, so based on the given integration, so we have triple integral. So your integrand here, so you have to find out this into the spherical function. So x squared plus y squared plus z squared is equal to rho squared. So rho square is the integrand, and dv is rho square sine phi d rho d phi d theta. Okay, so theta 0 to 2 pi and phi 0 to pi over 4, and rho is 0 to square root 8. So now we can solve the triple integral. So now we simplify. So you have rho square, rho cube, rho 4 sine phi d rho d phi d theta. Okay, so now I don't want to complete this, so please complete yourself, because I think the integration is not so complicated. So you just integrate the rho 4 d rho, so you will get rho 5 over 5, and after that you have to integrate the sine rho sine phi d phi. So just integrate sine easy, and then you can just evaluate, and we'll get the answer. So I'll just give you the solution here. You can leave your answer in terms of pi, or if you just multiply this by the pi, and you will get this. If the question asking for give your final answer in terms in 4 decimal places, so you have to give this particular value. Otherwise, you can just leave your answer in this form. So this one, maybe the a bit messy part is when you replace the row, there is a square root 8. But the process of integration, I don't think it is so complicated. Okay. Okay, look at the second one. So first, I want to find out the integrand in spherical expression. So the function in terms of x, y, z, which is the integrand, is given by square root of x squared plus y squared plus z squared. So in terms of rho, phi, and theta in spherical, then this becomes rho. Okay, so then we have to find the region. So as you can see here, we have again xy solid. So we have xy solid, where your region is lying on xy plane. So in this case, y is constant, 0 to square root 2, and x is a function given by y, square root of 4 minus y squared. Okay, so then to determine the curve on the xy plane, so here we can rewrite this into an equation. So you have x equal to square root of 4 minus y squared. Then this, of course, you need to rearrange, otherwise we have no idea the curve looks like. But please bear in mind that x is always positive. So you have x squared plus y squared equal to 4. So you have a circle, semicircle, because x only positive. Okay, and also you have the x equal to y, or y equal to x. So now we want to sketch the region. So your region is part of this, the semicircle. So I draw the complete circle first, 2, 2. Okay, so y, x. Okay, so I read for the y first. I read for the y. Y is only smallest y is 0, the highest y. Okay, y constant. So when y constant, then we have to draw the horizontal line. And that line is lying between 0 and square root 2. Okay, so but it's okay. I have to sketch whatever the curve first. So I will sketch the curve. So now the second curve is the line of y equal to x. So the line is of y equal to x. This one. Okay. So this one is x equal to y, and part of the circle. So now the way, so you have to be careful for this particular example, because we have no idea then what is our region looks like, right? Okay, then you have to back to the limit given. So the limit says that the y, we have to draw a line, horizontal line. So y always smaller, y in the lower bound is y0, so meaning that you don't have the curve down there. Okay, so we don't want y negative. So y cannot be negative, meaning that we need to erase this, because we don't want y to be negative. So no y should be negative. Okay, so y, the line here, the horizontal line is lying between 0 and SSCE2. Okay, so SSCE2, for the SSCE2, so that this is 2. Okay, I will check. Okay, so this is 2. So where is the SSCE2? So so we know that when for this line, when x equal to 0, y equal to 0. When y equal to SSCE2, x also SSCE2. Okay, but so we look at the x then. So the smallest the lower bound of x is the straight line. So the lower bound is the straight line, this one, and the upper bound is part of the circle, part of the semicircle. So we have a very small region here. Okay, so meaning that where is the set to? So actually it looks like, okay, maybe we can find out. So when they say that the highest y is set to, and y is the, so when y is square root 2, so that the x also square root 2. So the line is this one. So this is square root 2 and this is square root 2. So you have a very small curve there. It's very small. Maybe I need to enlarge. Okay, I will redraw it. Okay, so now I resketch so that you have a larger region. Okay, so this is our previous sketching, so I'll make it larger. So as you can see here, you have to shade the area, right? So based on the limit given, so your limit is right over here. Okay, so you have the y constant. So I draw the horizontal line, and the line is lying between 0 and 2. Okay, and then x, when you read x from the left to the right, so the lower bound is given by this is lower bound given by straight line, and the upper bound is given by the semicircle. So meaning that your region is over here. Okay, so that is your region. So then it looks like you have to, from the region on xy plane, only will give you the theta, because you want to solve them using spherical coordinate. So you have to find the theta, meaning that, I repeat, on the xy plane you can only have the limit of theta. So now we want to get the limit of theta. So this is your region. So obviously your region is passing through, part of your region here can be origin, right? So the smallest theta, I mean this line, x is positive. Okay, so the smallest theta is, because the region here is, part of the region is the x-axis, right? The line of x-axis. So your theta will be 0. And the highest theta, you have to find the theta. So you have to find what is this line in cylindrical or in polar coordinate system, polar. Okay, I think on the previous examples, long time ago, I show you how can we get the theta from this line. Okay, so y equal to x is the line, the equation of this line in Cartesian coordinates. So we want to get the theta. Okay, so you have to convert into polar. So y is r sine theta and x is r cos theta. So r can be cancelled out. Sine theta over cos theta 1. So tangent theta is 1. Theta is inverse tangent 1 will give you pi over 4. You have 45 degree. So meaning that the highest, the theta for this line is 45. So y equal to x and theta equal to pi over 4. They are actually the same curve, but different coordinate system. This one in Cartesian and this one in polar. Okay, now we can see that the limit of theta is 0 to pi over 4. Okay, so we're done for the theta. So to get the rho and phi, you have to look at from your solid. So for spherical, it's not the same as cylindrical. For cylindrical, you can have the r and theta on the region, but z you have to find out from the solid. But in spherical, you can only have your theta on the region. But another two variable, you have to find it from the solid. Okay, so now for other phi and theta, then we have to investigate what is the solid looks like. So to get the solid, then you have to look at your example here. So limit of z. So limit of z given by 0 to square root of 4 minus x squared minus y squared. Z0 is a floor, and this will give you z squared plus x squared plus y squared equal to 4. This is a hemisphere. It is hemisphere because they're always positive. Hemisphere with radius 2. And you have only a hemisphere. So your solid is bounded by the hemisphere and the plane z equal to 0. So you have a solid. So this is 2, 2, 2, and 2 on xy z plane. So that is your solid. So from the solid, you can determine the phi 0 to pi over 2, 90 degree, because you have hemisphere here, where your angle is 90 degree. 90 degree. Okay. Okay, and then what else? Rho. So rho 0 to 2. Now we can substitute. You can rewrite the triple integral into a spherical coordinate. Your triple integral in spherical becomes this form. So then please get your answer yourself. Okay, so I didn't provide you the step-by-step answer. I just give you the final solution. So I don't think for you this is so complicated, right? But this is not so tedious, but you need to integrate one by one, and please substitute with the corresponding limit given, and the final answer is pi.